We can finally define the Newtonian Sobolev functions using the notion of upper gradients. We say that the Borel function that is defined into the set of non-negative extended real numbers is an upper gradient of another function defined into extended real line if for every non-constant rectifiable curve the difference in values of u at the two ends of the curve is less than the path integral of the Borel function rho. The requirement that this rho be Borel guarantees that this integral will be well defined. We've talked about these in previous videos. And the reason to require non-constant rectifiable curves is that we use this convention, and we will keep using it throughout, that left-hand side is plus infinity if not both finite, not both values finite. So we don't care if they are both plus infinity or both minus infinity or one of them only is infinity. Whenever we hit any inconvenience, we will declare the left-hand side to be equal to be plus infinity. And if we did allow constant path, then this inequality cannot be sustained, as the path integral of even infinity over a constant path will be 0. Also notice that we could say that we could replace that for every rectifiable curve with every arc length parameterized curve, or for every Lipschitz. So if we change this rectifiable to Lipschitz, or even to arc length parameterized curves, we won't lose anything, because every rectifiable curve can be reparameterized to be Lipschitz and also can be reparameterized to be arc length. And on the other hand, this quantity, of course, won't change under parameterization, neither will this one, because the very definition is using the arc length parameterization, which does exist for rectifiable curves. So the more important observation here is that upper gradients are purely metric objects. So an upper gradient only use metric of the space. In fact, up to this point, we've never even mentioned that there is a measure on our space. To define the Newtonian Sobolev functions, though, we do want to bring in some measures. So we equip the space, metric space XD, with a measure. So and we want some conditions. For example, we want it to be a Borel measure, so that there is some connection between the metric and the measure. And also, let's say we don't want measure to assign infinity to every set or 0 to every set. So we can say locally finite, non-trivial Borel measure. Then the LP space of functions is defined the usual way. It's defined the usual way with this LP infinity norm understood. So LP understood as the LP norm of functions against this measure. Now consider a collection of functions on the space. Consider all measurable, which now is a meaningful adjective, measurable functions from x into r tilde, such that they admit at least one upper gradient with LP integral of that upper gradient rho, with LP norm of that finite. Remember that every function, even not measurable ones, have upper gradients. in particular, rho constant equal to plus infinity, per definition, is an upper gradient. But of course, we want more tame upper gradients. That's why now we're restricting to only those functions who at least have some upper gradient with finite LP. And then on these functions, we can define a norm. So the N1, say, norm of this, by the way, I'm restricting to the case P between 1 and infinity for now. And this we define to be the LP norm of U plus the smallest LP norm that you can have among all upper gradients. So where infimum is over all upper gradients, of course, of U. So the collection of measurable functions that I considered are exactly those where this N1P norm is finite. So there is an example that I will construct in next lecture. Despite its look, it quite takes some time to really construct such an example. So there exists a measurable, of course, function, a measurable function that is non-zero. It's not the zero function, but the norm N1P of that is equal to 0. This, of course, forces U to be 0 almost everywhere because, in particular, LP norm of U is 0. What this shows is that with this norm, the collection of functions that I considered will not produce a normed space, let alone a Banach space, which is the ideal thing we want. So this does not, N1P norm does not even define a norm on this space because the norm of some non-zero elements are 0. And as is typical from abstract theory, we can produce a normed space by quotienting out under this equivalence through the norm. So we define the Newtonian Sobolev space on the metric space XD, now equipped with the measure, to be the collection of all U such that U is measurable and N1P norm of U is finite. That means it has some LP integrable upper gradient. So that is the collection I considered already, but now we quotient out with this equivalence where U is equivalent to V if and only if U minus V N1P norm is equal to 0. So you can check that now. The equivalence classes N1P, so let's put it as an exercise, maybe, that N1P of X, for short, we drop the mention of D and measure with this norm, and 1P is a normed space. So this is now a genuine norm on this space. Therefore, N1P is some equivalence classes of functions. Very important convention, again, that we will follow throughout is the following, that we will always work with everywhere defined functions. So even in this situation, we don't really identify functions, even if this holds. So to us, u and v will always be different functions, and that will have important consequences. Even in the classical Sobolev theory, if you want to talk about more detailed properties of Sobolev functions, you don't want to identify them if they differ on a set of measure zero. And my next example will emphasize this in a very compelling way. So we will always work with everywhere defined functions. Genuinely defined at every point. And with that, I can now tell you my example 2, which hopefully will justify why we are so careful with where the functions are actually defined. And the example's message is that there exists u measurable that is almost everywhere zero. It's basically zero function, but not in n1p of x for any p in this range. And this is, again, in contrast to the classical Sobolev theory, where because we identify functions up to sets of measure zero difference, this function u will belong to the classical Sobolev function space. And this also emphasizes the importance of the correct representation of functions. This example should be the warning to keep in mind that we do not blindly alter functions even on sets of measure zero. Maybe you're safe often in the classical Sobolev W1P space, but never in Newtonian space. And that is one of the subtleties of the Newtonian Sobolev functions. So what is this example? Let x be R2 with the Euclidean distance and the measure being the usual Lebesgue measure. And my function u is, as explained, zero in fact almost everywhere except along one line. Let's say from with the height 1. So from 1, 1, and then 1, 0. But just along this line, let your function be equal to 1 if x is 1 and y is between 0 and 1, and the function is 0 other y's. So this is an almost everywhere zero function. So notice u of x as a vector is 0 almost everywhere. So we want to prove that this function is not in any n1p. So fix p between 1 and infinity. We need to show u has no upper gradient with LP norm of that finite. And that would definitely mean that u is not in the Newtonian Sobolev class, which from off to go is built out of those functions that do have this property. Okay, but why does u admit no reasonable no integrable, p-integrable upper gradient. So to convince you of this, I want to take another line parallel to this one, starting at 1 minus delta. So with the delta gap, and I only consider those curves that horizontally in the obvious way connect this. So this is one of those curves which, let's say, is gamma y based on the height that it has. So we have many parallel such lines connecting these two. But suppose that, so let's go back to the proof. So suppose, now that we have fixed P, so suppose rho from x, which is R2, into 0 plus infinity is an upper gradient of u. Then in my picture above, so then for every y in this 0, 1, the integral of over gamma y of rho ds, which is really integrating rho against the L1 measure on this segment. Because it's an upper gradient, it should be bigger than u evaluated at 1 minus y, 1 minus delta and y minus u of 1 and y. But this is 1 minus 0, this is 1. So along every one such segment, this integral is bigger than 1. Now we can do a Fubini's theorem. So by Fubini's theorem, we get that 1 is less than or equal to integral from 0 to 1 dy. So we add all these quantities on y. So gamma y rho dl1, which then is just nothing other than integral rho on this box. This Q being the box 1 minus delta to 1 cross 0, 1. So a box of side delta and height 1. Okay, and this is against the Lebesgue measure. And now I can use Hölder's inequality to see that this is rho to the power p d mu to 1 over p. And then I'm using like rho times 1. And this will be then measure of q to 1 over q. From which it follows that I'm using here the fact that p is strictly bigger than 1. I kind of didn't check the case p equal 1, so forgive me for that. Let me go back and say I want to do only p bigger than 1. But I'm pretty sure this space shouldn't be in n11 either. Okay, so this means that measure of q, which is delta times 1, so delta to negative 1 over q, should be less than or equal to integral rho to the power p d mu over this q to 1 over p, which is definitely less than, okay, less than integrating over, so minus p over q. We don't need that, sorry. So this is just less than LP norm of rho over the whole space X. But delta was arbitrary, which forces that the LP integral of rho b plus infinity. So we showed that for any upper gradient that you take of this u function, it's not in LP. Thus, u admits no LP integrable upper gradient, which then means u is not in N1P of x, according to our definition. So we have a function that is zero almost everywhere, but this particular representative of that does not belong to the Newtonian space. So it has some other representative, in particular u being zero everywhere. If we change u on a set of measures 0, then it ends up in N1P. So that was my second example that I did, but my first example, again, will be done in next lecture, where I give a measurable function that is not 0, but the N1P norm is 0, which was the reason for the quotienting in definition of N1P space. I want to end the video, but I kind of feel a bit not happy about the fact that I had to sacrifice this p equal 1 case. Somewhere we should be able to push this integral of rho all the way up. So could it be done with integrating that here? So this is Fubini. Okay, maybe I'll think about it and let you know later, but at least it's not the central point to our example, which says that you cannot arbitrarily change a function even on a set of measures 0 and still expect to be in N1P. Okay, until next video, have a good one, and thanks for watching.